Okay, so today we're going to start in on chapter 5.4 of your book, which is logarithmic functions. And we'll try to be a little bit quicker about this one this time, so let's get into it. So far for every operation, we have seen how to perform the inverse, or how to undo the operation. To undo addition, we subtract. So if you have a plus 2, you can subtract 2, and that will get rid of it, get you back to 0. So like if you had x plus 2, right, you can subtract 2 to solve for x. And obviously vice versa. To undo multiplications, if you have like 2x, you can divide by 2. Those will cancel out. To undo squares, so if we have like x squared or if we have x cubed, we can take the root. So in the case of squares, it's the square root. In the case of cubes, it's the cube root. In the case of x to the fourth, it's the fourth root, and so on and so forth. So now the question is, how do we undo an exponential function, such as 10 to the x? At this point in time, we don't have the tools to solve something like this. 10 to the x equals 270. If anybody in this class can tell me how to solve this question without watching the rest of the lecture video, then I'm impressed you paid attention at the end of Algebra 2. You might have covered this, I'm not actually sure. So the answer, spoiler alert, is logarithms. So in general, there are 3 major types of logarithms, which are common logarithms, also known as log base 10 logarithms, Base-a logarithms, and natural logarithms. You're probably going to hear me referring to these throughout the video as just logs, so log base 10, log base 2, log base 3. That's just the way that mathematicians and math people in general shorten these out. So let's look first at common logarithms, also known as base 10 logarithms. These are effectively the inverse of raising 10 to the exponent of x. So what you're asking here is 10 raised to what power equals this number? Like if we go back to our last one. So if you take the log of 270, what that's doing is that's solving for this x. Now, in the olden days, people had these giant charts of like all the different logarithms. There's a reason that they used log base 10. It's a lot easier to figure out what log base 10s are, mostly because if you have things like, 10x equals 100, well, that's easy. That's going to be x equals 2. And then if you have 10 equals 1,000, then x equals 3, so on and so forth. So it's one of the easier ones to solve for. But there used to be big book charts and you just had to look through and find the right number. So it got pretty awful. But nowadays we have handy dandy little calculators, and even your phone calculator has a way to do logarithms in it. So this function is simply a log x or a log base 10 button on your calculator. You don't have to go through looking through charts and stuff to figure out logarithms. Simply put, I should say put, not but, log x equals k if and only if x equals 10 to the k, where k is a real number. So this is going to make more sense when we see some example problems. So really quick, I want to talk about this notation right here, this log of x. In general, if you see a log with no base after it, there's an implied 10 here. If you see log by itself, it's implied that there's a 10 as the base. In general, the way we write logarithms is with some kind of base. And this is telling you what number it is, right? So this is basically saying we want to solve 2 to the x equals some number. So if log base 2 of x equals, 7, then we're saying 2 to the what equals 7. Right, this is just solving for that. So there's usually going to be a base. If there is not a base like there is here, then it is just assumed to be a 10. So log of 100 equals 2 because 100 equals 10 squared. So the log of 100, what this means is that log of x, so that would be here, 100, equals 10 to the 2, because that's the answer to the question. So log equals 2, right? 100 equals 10 squared, etc., etc. You can think of a common logarithm as asking the question, 10 to what power equals this number? So log of, let's say log 150 of, is asking us basically 10 to what number equals 150? So, I thought there were supposed to be some calculations here. Oh, right. So really quick, there are a couple formulas that you need to know before we move on. For these right now, they're using base A notation, but it works for 10. So you can just substitute a 10 wherever you see A. But there are a couple of additional formulas that are useful in solving exponents and logarithms. We're going to work with both of these later on, but you're going to want to write them down right now. And these apply to all types of logarithms. So they apply to log base 10 logarithms, they apply to log base A algorithms, and they apply to natural logarithms. And they are log base A of A to the X is equal to X, and A to the log base A of X equals X. Basically, again, because a log is asking what number A, the base, needs to be risen to give you this, right? This is asking you A to the X equals A to the X. What is X? And we're saying that, well, X equals X, right? So this is just a simple formula. This one here is saying A to the whatever number is log base A of X equals X. This is kind of a complex formula, but once you get used to using it in practice, it won't be too terrible. It looks like a lot more variables and confusing things than it actually is, but basically, if you see the same number here and the same number here, then this is your answer. Is the simple way to think about it. We'll look through some examples. You'll get plenty of practice with it. So the first few, these ones, I don't know why there's a slash here. Let's ignore this. That's not what that was supposed to be. Because it's supposed to be 1 over 1,000. Okay, here. Let's redo this like this. So we're looking for the log of 1 over 1,000. So remember, because we don't have any base here, these are all implied base 10s. So this is asking us 10 to the x equals 100,000. And the question is, what is x? Well, 100,000 is equal to 10 times 10 times 10 times 10 times 10, or 10 to the 5th. And since we're looking for the exponent, in this case that is 5, so the answer to log base 100,000, or log base 10 of 100,000 is 5. Now you could also just plug this into your calculator and it would give you 5 right away, but we can calculate it by hand as well. This one's a little bit more complicated. We're asking 10 to the what power equals 1 over 1,000. So in this case, you've got 1 over, this is 10 times 10 times 10, or 10 to the 3rd. So 10 to what power equals 1 over 10 to the 3rd. And hopefully, if you remember enough from exponents, you know that 1 over something raised to a power is just that same thing raised to the negative power. So that means that 1 over 10 to the 3rd is equal to 10 to the negative 3rd. So that means that 10 to the x equals 10 to the negative 3rd. So x equals negative 3. So in this one, we again have x equals negative 3. And again, you can plug that into your calculator and double check it. This one's a little bit funnier. This one's kind of a more enjoyable problem, I think. It's asking you 10 to what power equals 1. And hopefully, everybody knows off the top of their head that in order to get 1 out of something being raised to a power, the power must be 0. So log base 10 of 1 is 0. Interestingly, log base 2 of 1 is 0. Log base 373 of 1 is 0. It doesn't matter what the base is. If you're taking the logarithm of 1, the answer is going to be 0, unless the base is 0, in which case it's undefined. But that's not relevant right now. Okay, this last one, we need to actually go back and use one of our formulas here to solve this. This says 10 to the x equals the square root of 10. Now, we could go ahead and just solve this out by using mental math, right? We're asking 10 to what power equals 10, or the square root of 10, and hopefully you remember that square roots are just 1/2 power. But if you wanted to use a calculator to solve this, what we can do is we can go back and we can look at this. So we have a log base 10 of 10 to the x, right? Log base 10 of 10, oops. The log, hold on, this is what I meant to do, sorry. Oh, I just deleted everything, oh well. So log base 10 of 10 to the x would equal x. So if we take the log base 10 of both sides, so we'll just go log of 10 to the x equals log square root of 10. We get x equals, and you can type this into a calculator, see what you get. But you're going to get x equals 1/2. We'll look at more example problems of that in a little bit. Okay, let's move on to base-a logarithms. So let's look at the example of where you'd want to use these. If we have the question 3 to the x equals 27, and we want to solve this for x, hopefully everybody can do this already, just like in your head. You should know that 3 raised to the power of 3 is going to be 27. But here's a more complicated example. We've got 3 to the x equals 30. Now, again, hopefully you guys can all kind of infer that this is going to be somewhere between 3 and 4, but actually narrowing this down is going to be really difficult without using mental math. So in order to solve this problem, we need to use a logarithm function with a base of 3 rather than 10. So that's what base-a logarithms are. So in this case, what we do is we take the log base 3 of both sides of this equation. So we're doing that goes there. So basically what we're saying is log base 3 of 3 to the x equals log base 3 of 30. And if we go back to our formulas way back here, we see that the log base a of a to the x is equal to x. So in this case, we have a log base 3 of 3 to the x. So these numbers are the same, which means this is equal to x. Basically, log base 3 of 3 to the x, all of this stuff cancels out, and you're left with just x. So we have log base 3 of 30 equals x. We can solve that in our calculators. I'm going to go ahead and type that out. Actually, let's see if my phone calculator even has a log that I can change the base on. Oh, it doesn't look like it does. That's cool. Okay. Well, luckily your graphic calculators all do, so you can just type this in there and you'll get an answer that should be around like 3.1, something in that basic range. Now these ones we can all do by hand. So here we've got log base 2 of 8. Now remember, this is asking 2 to the x equals 8. You can also just type this into a calculator. Again, you'll be able to get this solved right away. But 2 to the x equals 8. This means that x is going to have to equal 3. Right? 2 to the third is 2 times 2 times 2. 2 times 2 is 4 times 2 is 8. Log base 5 of 1 over 25. That means 5 to the x equals 1 over 25. And then we can solve this for x. This is, of course, x equals negative 2. 25 is 5 squared, but it's on the bottom of a fraction, so we know that it's going to be a negative power. So x equals negative 2. And again, if you don't know how to get to the fraction form of this from here, you should probably go back and review exponents a little bit. But again, this is something I'd be happy to talk about more in class if you guys need me to. So these two are using our problem or our equations from before. So remember, log base a, hopefully you guys all have this written down, of a to the x equals x, and a to the log base a of x equals x. So in this case, we have a log base 6 of 6 to the negative 1.3. And so we already know the answer to this is just going to be negative 1.3, right? This stuff, again, basically just cancels itself out. You have a log base 6 of 6, log base a of a. So whatever the power is the part that we're going to keep on this side. And in this case, that's the negative 1.3. And then the last one, the same basic idea, except now we're using this function here. So we have 5 to the log base 5 of x plus 8. This one we can't actually solve for x or anything. There's not an equal sign in this. So the answer that we're going to get is x plus 8, as that is the x portion of this logarithm. Okay, and I believe that's it. Oh, no, we're going to talk about natural logs, right? So natural logs are the last thing that we're going to talk about on this one. Stuff's pretty easy. Natural logs are basically the same as base-a logarithms, but instead of having a base that can be any number, the base specifically is the number e. So that's Euler's number. We talked about that yesterday with continuously compounding interest. This comes into play a lot when you're looking at things that continuously compound. So it's mostly going to be in story problems, which luckily for you guys, I'm not going to assign very many, but still it's something that you want to be able to know. So again, remember from last time that E is about equal to 2.718. And natural log is abbreviated ln. So on your calculator, you should have a button for this. I think it's even on my phone calculator. Yeah, it is. So ln, that means natural log, which is the same as log base e. Don't ever do this. Don't ever do log base e. Just use ln. It's not wrong. Like, this will still work. It's just that you're doing weird things that you don't need to do. It's a special type of logarithm. So in this case, we have natural log of e to the negative 3.1 equals negative 3.1. Again, since I said that natural log is equal to log base e, we have log base e of e to the negative 3.1 using that formula that says log base a to the x equals x. This whole thing cancels out, so we're just left with negative 3.1. Okay, so let's see how to solve the following. Wait, what? Oh, okay. So now we're working for inverses. So now what we have is, in this case, this is a log base 10, right? There's no number here, so it's implied 10. This is log base 10 of x equals 3. Now, solving this is a little bit more difficult to kind of come up with. But what we're going to do is we're going to use this formula that was a to the log base a of x equals x. Now, in order to do that, what we have to do is we need to take both of these sides, and we're going to use both of these sides as our exponents this time. So we're going to do 10 to the log base 10 of x equals 10 to the third. Now, what this does, since now we have an a to the log base a of x, or 10 to the log base 10 of x, this part cancels, and we're left with x equals 10 to the third, or x equals 1,000. So it's kind of a neat little trick, but that lets us solve it. So if you're thinking about this as like an equation, if you're wondering why we can take 10 and raise it to the power of both of these things, as long as we take the same base on both sides, it's not actually going to change our equation. And I can prove that really quick. So if we do 5 minus 2 equals 3, you guys already know that this is true. If I take 10 and raise it to these powers, you're going to find that it's going to be the same exact thing. So if we do 10 to the 5th, and then when you're doing these exponents or minuses, you have to do a divide sign. So we're going to do 10 to the 5th divided by 10 squared equals 10 cubed. 10 to the 5th is 1, 2, 3, divided by 100 equals 1, 0, 0. And we're doing 100,000 over 100. We can cancel 2 of the zeros. We're left with 1 with 3 zeros, which is what we have on this other side. So just a really quick proof that you can actually take a base and raise it to a power on both sides, and it'll still keep you with the same answer. So all of these are going to be a little bit trickier to solve, but we're going to go ahead and go through how to do each one of these. If you can solve all of these types of problems, you're probably going to be pretty much fine on all of your homework and on the test section for this. So this one, first of all, we need to, like we do with any other function, we need to isolate our variable. In this case, the variable is part of this exponential function. So we need to get the 2 to the x by itself. So we're going to start by adding 7 to both sides. That gives us 3 times 2 to the x equals 27. We'll divide both sides by 3, get rid of this. We're left with 2 to the x equals 9. So then what we want to do here is we want to take the log base 2 of both sides. If we take the log base 2, 2 of 9. So we'll have log base 2 of 2 to the x. And again, this is one of our formulas. These are going to cancel. Equals log base 2 of 9. So x equals log base 2 of 9. And this should be just a little bit over 3. I don't, again, have a graphic calculator, so I can't solve this right now, but it's going to be just a little bit over 3. Okay, the next one says log base 2 of x equals 5. Now, in order to solve this one, what we need to do is we need to use not the formula we just used here, which is the log base a of a to the x, but instead we're going to use the a to the log base a of x. And again, I really hope you have these formulas written down, otherwise you're probably going to be getting lost every time I talk about any of these things. So we're going to raise 2, since this is our base for our exponent, take 2 to this and 2 to this. So this gives us 2 to the log base 2 of x equals 2 to the fifth. The 2 to the log base 2 cancel out, and we're left with x equals 2 to the fifth. 2 to the fifth is 2 times 2 times 2 times 2 times 2. So this is equal to 32. So x equals 32 for this one. Okay, and then we're going to do a very similar thing here. This one, we've got a log base 5 of x. So we're going to take 5 and raise it to this power. We're going to take 5 and raise it to this power. So again, this part will cancel. And we'll be left with x equals 5 to the negative 2. X equals 1 over 5 squared. X equals 1 over 25. Once again, if you don't know how to solve this right here, please go review exponents or talk to me in class, because that is very important for this section. But again, this is just 1 over 5 squared, so that's 1 over 25. Then the last one, we have the natural log of x equals 4.3. So this time we're going to do e to the power of both sides. So we get x equals e to the 4.3. And again, I would just plug this into a calculator and solve it. But we're going to call it good right there right now because I do not have a calculator. Actually, hold on. I might have an e to the x button. Let me check. Oh, I do. Okay, so 4.3 e to the x, or about 73.7. If on a test you wrote the answer like this, I'd probably accept that because honestly, that's more correct. We have to round if we're going to use a decimal. So in this case, this is perfectly fine. Okay. I believe that's actually it for this one. So again, if you have questions about this, please talk to me about them in class. Friday is going to be all day, is just going to be a day for questions. So you guys are welcome to come by and ask whatever you have, whatever problems are bothering you. But otherwise, I will see you guys later.